Until now, I think you have a basic understanding of 5G new architecture. But only new architecture is not enough to support such a strong network performance. Let's see some typical technologies of 5G air interface. In this chapter, we will discuss about 5G new air interface technologies. Traditional network mainly focus on mobile internet service and lies IoT or Internet of Things applications. That's not enough for 5G. 5G air interface should be more flexible and support high data rate and higher spectral efficiency. First one, large bandwidth. The large bandwidth means have more spectrum resource for high frequency. But high frequency will bring coverage issue. This issue can be solved by using uplink and downlink decoupling technology. Flexible frame structure is one typical technology to support low latency. Other three technologies can improve spectral efficiency and further increase the single-user data rate. Let's see them one by one. Let's review the 5G spectrum together. 5G spectrum include frequency range 1 and the frequency range 2. FR1 can separate into sub-3G, which is from 0 to 3 GHz, and sub-6G, which is from 3 to 6 GHz. And the millimeter wave have rich spectrum resource and a higher frequency than frequency range 1. And there is one question. Do you remember what's the maximum bandwidth can be supported by C-band and the millimeter wave? Yes, 100 MHz for C-band and 400 MHz for millimeter wave. Attention please. C-band and the millimeter wave are all TDD system. TDD, time division duplex. That means uplink and downlink must use the same frequency for the data transmission. As we know, the higher frequency is, the higher path loss is. And always, the base station transmit power is higher than the user equipment transmit power. So when uplink and downlink use same frequency, there is one issue. Let's see the following examples. Frequency is C-band in different scenario and with different rate. The coverage distance of uplink and downlink are different. But uplink is always smaller than downlink. That means unbalanced downlink and uplink coverage. What problem will be caused by the unbalancing? At unbalancing area, base station cannot receive the uplink signal from user, so transmission will fail. So how to solve this problem? If this issue is caused by frequency, why not change the uplink frequency? The solution is uplink and downlink decoupling, or SUL, supplementary uplink. The left figure shows the coverage gap between uplink and downlink. When 5G base station deploys 3.5 GHz frequency, the coverage of uplink is the yellow area, and the coverage of downlink is the green area. How to supplement the gap between the green area and the yellow area? In the gap area, the uplink will use low frequency, which is provided by 4G base station, just like the right figure. The blue area is supplemented by 1.8 GHz uplink spectrum. So for this SUL solution, at a yellow area, user will use 3.5 GHz for both downlink and uplink data transmission. When user go to the unbalancing area, the user will shift uplink to lower frequency to enhance the uplink coverage. But the downlink frequency is still 3.5 GHz. So that is the 5G spectrum and how to solve the coverage problem caused by high frequency. Antenna number also can affect the coverage, and more antenna will bring other gains. That's called MIMO or MISIM MIMO. What's MISIM MIMO? MISIM literally means large scale. When the number of antennas in a solution is greater than or equal to 16, the solution can be termed as massive MIMO. If the number is smaller than 16, just a normal MIMO. Let's see how massive MIMO works. Massive MIMO relies on the interference and the intersection principles of wave. When massive MIMO is used, it weighs signals and adjusts the direction of each wave to form a directional beam, as shown in the following figure. There are two antennas in this figure. If signals transmitted by the two antennas are not weighted, they are transmitted in the default state. The green circles are the wave crests, and the purple points are the wave troughs. When wave crests intersect, the signal strength increases. When a wave crest intersects with a wave trough, the signal strength decreases. If a user is located at the axial wire of the two antennas, the signals received by the user are enhanced. However, if the user is located at the intersection of wave crest and wave trough, the received signals with poor quality. On the live network, as we know, users are mobile and may not always be located at the axial wire of two antennas. Therefore, signals must be weighted to form a directional beam to direct towards the user. This is one feature of the massive MIMO. And what are the other benefits of massive MIMO? First, a regain. That is a power gain achieved by combining signals from different antennas based on the correlation between signals and the non-correlation between noises. Signal combining increases the signal to interference plus noise ratio, or SINR, of the combined signal. Next one, beamforming gain. That can cover both horizontal and vertical directions. It can implement three-dimensional beamforming, or 3D beamforming, which can cover high-rise building easily and also can cover sky for joint communication. Multiplexing gain. Now, 16-layer beam multiplexing can be achieved in the downlink with the prerequisite of user pairing. After users are successfully paired, the GNODB allocates the same resource block, or RB, to these users, which means that the resource block can be shared by these users. This way, the capacity of the entire cell will increase. Note that the capacity improvement by massive MIMO is the cell level instead of the user level. And the next one, diversity gain. By increasing the antenna number to improve reliability of data transmission. And this is the gain of the massive MIMO. And let's move on to next technology, polar and LDPC coding. The two coding schemes apply to 5G eMBB scenario. They are determined in 3GPP release 15. What about their performance? First, compared with convolution code used in early 3G stage. What about their performance? First, compared with convolution code used in early 3G stage, polar code requires a lower signal-to-noise ratio given the same block error rate. Also, polar code results in a higher encoding efficiency under the same signal-to-noise ratio, which means that less redundancy is required. If less redundancy, it means the size of the packet will be smaller. The decoding efficiency of low-density parity check code, or LDPC, is similar to that of the turbo coding in low bitrate scenarios. such as small data packet coding or low-rate coding. The TURB code is used to encode traffic channels in LTE. When the bit rate is high, the LDPC outperforms TURB in coding and decoding efficiency. Higher decoding efficiency leads to higher peak rate and lower power consumption. The LDPC code can better meet data decoding requirements for 5G services, which features a high rate, a large bandwidth, and low power consumption. So in 5G eMBB scenario, the control channels use polar codes, but the traffic channels will use LDPC codes. Now let's move on to the next efficiency improved technology, 256 QEM. 256 QEM is a modulation technology. QEM is short for quadrature amplitude modulation. What's modulation? Modulation is categorized into digital modulation and radio frequency or RF modulation. RF modulation is implemented by the RU or AAU. The main function of RF modulation is to transfer baseband signals from the low frequency to the high frequency and then transmit the signals over the air interface. The modulation we emphasize today is digital modulation because it affects the carrier efficiency of the entire cell as well as the peak rate of users. What's digital modulation? Digital modulation is a process of loading source signal data onto a carrier. In other terms, digital modulation is a process of describing different useful information by using different amplitudes, phase, or frequencies. Let's compare the modulation schemes in LTE and 5G. In the uplink, the LTE modulation schemes range from QPSK to 64 QEM. In the downlink, the highest order modulation scheme supported by LTE is 256 QEM, which is supported since 3GPP release 12. In the uplink, the highest order modulation scheme supported by 5G is 256 QEM. And in the downlink, the highest order modulation scheme supported by 5G is also 256 QEM, which is frozen in 3GPP release 15. There is a possibility that 1000 or 24 QEM will be supported in the future. Compared with 64 QEM in LTE, 256 QEM increases the peak data rate of users. The left figure shows 64 QEM and 256 QEM. And you can see 256 QEM used in 5G has 256 concentration points, and the 64 QEM used in LTE has only 64 concentration points. In 64 QEM, each point carries 6 bits, and each point in 256 QEM carries 8 bits. Ideally speaking, 256 QEM increases the peak rate by 33% when compared with 64 QEM. Okay, to sum up, 256 QEM modulation is more complex than 64 QEM. It's more mistakable during demodulation. So 256 QEM has higher requirements about signal quality. That means 256 QEM need more close to cell center. In order to guarantee the demodulation performance, when the user moves away from the base station, always sacrifice the data rate to guarantee the communication quality. The lower order modulation scheme is used. The descending order is 256 to 64 to 16 and QPSK. This is coding and modulation technologies that can improve the efficiency of the entire cell or increases the peak rate of a single user. Let's move on to the next technology, FOFDM. FOFDM is short for Filtered Orthogonal Frequency Division Multiplexing. FOFDM improves the carrier utilization. The main function of FOFDM is to optimize the filter. FOFDM can reduce the guideband requirement in 5G. Because guideband area cannot be used for data transmission, it's empty. So reduced guideband bandwidth means 5G can have more available resource for data transmission. Compared with 4G, 4G guideband is fixed value, that is 10% of the whole bandwidth. In 5G, this percentage is variable. It's based on the subcarrier spacing. What's subcarrier? Subcarrier is the smallest unit in frequency domain. 5G subcarrier spacing is flexible. That is the flexible air interface pneumonology. 4G only uses a single 15 kHz subcarrier spacing. That is, 5G pneumonologies are variable. 5G uses the mu parameter to indicate the subcarrier spacing. For example, when mu equal to 1, indicates that 30 kHz subcarrier spacing is used in frequency domain, and the transmission time interval, or TTI, is 0.5 milliseconds in time domain. Frequency and time just like the two sides of rectangle. When the area of the rectangle is fixed, if we extend one side, another side will decrease. So if we want to shorten the latency, we can choose smaller TTI. Configure different subcarrier spacing for different services. This is also one way to support network slicing in air interface. For example, for the delay-sensitive service, we can choose mu equal to 2. For the service which is not delay-sensitive, we can choose mu equal to 1. This is all of the content of this course. Let's make a summary briefly. In this course, there are two typical developments of 5G, new architecture and new air interface. Two kinds of network solutions, non-standalone and standalone. The mature 5G network solution is standalone. For the cloud-based service-oriented core network, SoC, totally 4 features: CUPS, SBA, slicing, and the native cloud. And in 5G, wireless network architecture is Cloud Run. Central unit and the distributed unit separation can reduce air interface latency. For the new air interface, large bandwidth and high order modulation can increase data rate. For enhanced uplink coverage, can use SUL, and massive MIMO technology can both increase the data rate and the coverage. And high spectral efficiency can be supported by FOFDM and pneumonology. That's all for this 5G advanced course. Thanks for listening. Bye.